Welcome to the first lecture of Chapter 9. So this is Chapter 9, Part 1. This will correspond to slides 1 through 32 in the main PowerPoint, if you're looking at that on Canvas. And this will cover Chapter 9 lecture worksheet pages 1 through 3. So Chapter 9 covers the Lewis model, right? The Lewis bonding model, as opposed to Chapter 10, which will cover the valence bond theory, molecular orbital theory, VSEPR, all of those kinds of things. So Chapter 9, though, focuses on the Lewis model, which you're likely familiar with from other chemistry courses. So today we're going to talk predominantly about ionic bonding, and then the rest of the chapter will be about covalent or molecular bonding. So chemical bonds, just in general, most matter in nature is found in the form of compounds, right? Most matter is not just, you don't see like magnesium just kind of sitting around or iron just kind of sitting around. It's usually found in compounds, which are two or more elements that are held together through a chemical bond. So the elements combine together or bond to fill their outer energy levels and achieve a stable structure. And so this stable structure that they're talking about is that 8 valence electrons, right? Elements combine so that they will have 8 valence electrons, which is why we see that noble gases don't make compounds very frequently, because they already have those 8 valence electrons. So there you go, noble gases, generally unreactive. So there are, though, we're going to see later in this chapter, actually, that noble gases will form some molecular compounds. So this is like kind of, right, this noble gases bit. Noble gases are mostly unreactive since they have those 8 valence electrons already. So the nature and type of chemical bond is directly responsible for many physical and chemical properties of the substance, like melting point and conductivity, right? So ionic compounds have different properties than covalent or molecular compounds do, where like ionic compounds have really high melting points, whereas covalent compounds have really low melting points and things like that. So the type of bond is responsible for those properties. So we have 3 different kind of types of bonding. So the first one is the one that we're going to talk about today, and this is ionic bonding, where sodium will lose an electron and give it to chlorine, essentially. So sodium forms Na+, and chlorine forms Cl-, and they form these types of structures that you're seeing here, where we have alternating positive and negative charged particles. So when we say salt is NaCl, right, that is telling you the lowest ratio of those atoms. So for every 1 sodium, there's 1 chlorine. This is not a discrete molecule. These are these crystal structures that have repeating patterns of sodium and chlorine, but this is telling you that for every 1 sodium present, there will be 1 chlorine present. You'll notice what we were talking about in the last chapter, that sodium, right, this neutral sodium is bigger than the sodium ion, than the cation, right? Because when atoms lose electrons, they become smaller. Cations are smaller than neutral atoms, whereas when chlorine gains an electron and forms this negative chlorine, right, this anion, it got bigger. So it's fair game, like if we saw, if you saw this, and I asked you to identify which of these is sodium and which of these is chlorine, you should know that the cations are always the small ones and the anions are always the big ones. Cations are smaller than anions. Our other type of bonding that we'll talk about pretty much for the remainder of the chapter after today is covalent bonding, also sometimes called molecular bonding. But covalent bonding is when atoms are sharing electrons in order to complete their octet. So like chlorine has 7 valence electrons and bromine has 7 valence electrons. When they each share one of those electrons, right, from an orbital overlap, they will have complete octets. So this is covalent bonding. And our last type of bonding, which is not as common, this is metallic bonding. In metallic bonding, we talk about a sea of electrons. And so it's just a repeating, metal, 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 metal over and over and over again. And they have electrons that can easily flow from one atom to the next. We're not going to deal so much with metallic bonding. We're really going to spend our time focusing on ionic bonding today and then covalent bonding for the remainder of the chapter. So, ionic bonds. Ionic bonds are formed between a metal and a nonmetal, right? That metal atom loses an electron, and it will give it, and it will form a cation, and it will give it to that anion, that nonmetal, which gains it. That ionic, bond is essentially just an attraction between that positively charged cation and that negatively charged anion. And so if we think about Coulomb's law, right, we've talked about Coulomb's law a couple times, the larger the charge is, so like a 2 plus, right, if you have something like a 2 plus or a 3 plus or a 2 minus or a 3 minus, right, the bigger that number in front of the charge, the stronger the attraction will be. Because if we're thinking about the energy of attraction or the force of attraction, and so it's Q, Q1, Q2 over R. So the bigger these charges, these Q's are, the bigger these are, the larger this energy or force of attraction. And then similarly, the smaller the ion, right, the smaller this atom is, so that would make the radius down here smaller. So if you have a small radius, then you're going to have a very large force of attraction, a very strong attraction. So when we're looking at things that form really strong attractions, we want large charge and little atoms. So small ions with a very large charge is what we're looking for when we want strong attractions. So here's some properties of ionic compounds. They form crystalline solids, and there are lots of different types of crystal structures. We are not going to learn the different types of crystal structures in this course. Someone else can torture you with that later, but they do form crystalline solids. They have a repeating pattern, like the solid I was showing you earlier, where that sodium and chlorine were alternating. They generally have very, very high melting points, right? They're solids at room temperature. They also have really high boiling points, right? You don't hear people talk about, boiling sodium chloride. That would be kind of unusual. So very high melting points, very high boiling points. They can conduct electricity very, very well when they are molten. So if you melt, right, if you melted a bunch of sodium chloride, just like took the salt and melted it, it would conduct electricity. The other way that it conducts electricity, which is more common, is when it is aqueous, right? If you stick some salt in water, then it floats around as Na plus and Cl minus, and these charged species allow electricity to flow through the solution. So they are really, really good conductors, but it must be either molten, which is how we get the technical definition of whether or not it can conduct electricity. We would melt it. Molten, or like I said, more useful for us is aqueous. And then these compounds are generally soluble in water. We do know that there are some exceptions, which we've talked about previously in the course, but in general, ionic compounds tend to be soluble in water. So here's a little bit about electrostatic forces. So if we again, thinking about sodium chloride, if you had a block of salt, right, just a big block of salt, and you hit it with a hammer, right, it would crack. You would think it would be weird if it would just kind of mush down or, something like that. But so the reason that it cracks is, remember that sodium chloride has this alternating pattern of positive and negative charges. These are all shown as the same size, just to kind of, have a simplistic diagram, but we would know that the cations should be smaller than the anions there. But if you hit it with a hammer, right, then the charges shift. So like these would all shift down. And when they shift down, now we've got positive next to positives and negatives next to negatives and so forth. And that, right, those like charges will repel. And when they repel, the crystal cracks. So this is why it's, the salt doesn't just mush, it will actually break. So like I was talking about a little bit earlier, if you have a solid ionic compound, right, just like you put some salt in a beaker and stuck a light bulb in it, there no electricity can flow because these ions aren't free, right? These ions are stuck where they are. And again, right, these, the sodium would be the small ones, the chlorines would be the large ones, but they're not free to flow through solution. If we melt it, right, we put it under really high temperature and we are able to melt our salt, now these ions can flow and they can move around, which allows electricity to flow through the solution, right, or the molten ionic compound. Similarly, if we dissolve our ionic compound in water, then the ions are also free to move around and allow electricity to flow. So electricity will not flow if if the ions are locked in place and it's just a solid, but if you melt it or if you dissolve it in water, the electrons can flow through solution and conduct electricity. So here's some melting and boiling points of some ionic compounds. This is just to show you that they have really, really high melting and boiling points. Okay, so I'm just going to kind of click through these. They're very high temperatures, right? These are in degrees Celsius. So if we think about water, right? Water is a liquid at room temperature, right? And so at 100, whereas, sorry, not 100 is not room temperature. At 20 degrees Celsius, water is a liquid. And the melting points of these compounds are way above 20 degrees Celsius, right? These guys are nowhere close to melting. You would have to heat it really, really high. What we're seeing, is the larger the charges and things like that, right? The bigger these atoms are, the harder they are to melt. So electrons are transferred in ionic compounds, right? They're always going from a cation to an anion, from a metal to a nonmetal. So they're being transferred. In ionic bonding, right? We looked at, in that last set of slides in chapter 8, we were looking at a table of electronegativities. So if you looked at the difference in the electronegativities of ionic compounds, you're typically getting an electronegativity difference, right? So if you subtracted them, it would be greater than 1.3. That's how we're going to classify things as ionic bonds. It's usually easier to just see, there's a metal and there's a nonmetal. That's an ionic bond. But if you were unsure for some reason, you could subtract their electronegativity values. Anything greater than 1.3 is going to be an ionic compound. And the formation of ionic bonds is always exothermic. Okay, and so this is because this is a favorable interaction. By forming these ionic compounds, right, both atoms are getting 8 valence electrons. This is a favorable interaction. So whenever you think of exothermic, it's things that, usually in nature like to happen. It's favorable. So the formation of ionic bonds, always exothermic, always energy is being released because now both atoms have 8 valence electrons. So here's that table of electronegativities that I was referencing earlier. So again, if you were to compare two things, and you could see that they were, ionic just based on the subtraction. Essentially, they typically have an electronegativity difference greater than 1.3. Some will say 1.4. Either way, it's kind of a rough estimate here. So like if we took, sodium and chlorine, here's sodium. Here's chlorine, 3 minus 0.9 gives us an electronegativity difference of 2.1. This is a very ionic compound. So we have this octet rule. And the octet rule is that when atoms bond, they tend to gain, lose, or share electrons to result in 8 valence electrons. And so they'll usually end up with this electron configuration of something S2, something P6. Depending on, which one it is. This will give them a noble gas configuration, which essentially just means they have 8 valence electrons, right? So there's lots of different ways that this octet rule is phrased, but essentially they're going to figure out a way to get to 8 valence electrons. There are some exceptions, and we'll talk about exceptions all through chapter 9. One of the exceptions would be hydrogen, and lithium, beryllium, boron, all of these guys, they will not form an octet. they will form a duet, typically, like helium. Okay, so helium has an electron configuration of 1s2, and it's a noble gas, right? And so we said that the goal, right, was to have a noble gas configuration. While helium, its outer shell is full with those 2 electrons, and so hydrogen will do the same thing, and lithium and beryllium and sometimes boron will do that as well. So helium has 2 valence electrons. We call this a duet. We spend a lot of time talking about an octet, but a duet is fine too. So this is why lithium will lose 1 valence electron and form Li+. Hydrogen can share, right, which we'll get into more in the next set of slides, but it can share or it can gain 1 electron. If, it can form a hydride every once in a while, which I've mentioned a couple times in the course, but it will typically lose that 1 electron and form H+. Okay, beryllium will lose its 2 electrons, it will call, and it will be Be2+. It can do this. This is if beryllium forms an ionic compound. It will actually commonly share its 2 electrons in covalent bonds, and it will result in 4 valence electrons, right? If it takes its 2 and shares 2, those 2 with another atom, then it will have 4 valence electrons. So it can actually have less than an octet. Okay, so it can lose 2 and form Be2+, or it can share and have 4 valence electrons. For this reason, beryllium is fairly reactive. Boron can lose its 3 electrons and form B3+. That's kind of uncommon though. Usually boron will share its 3 valence electrons and it will end up with 6 valence electrons. This compound, this is boron trichloride. But again, since boron doesn't have 8, that tends to make it fairly, these boron compounds fairly reactive when we can do some cool chemistry with those. But if it was to form an ionic compound, it would lose 3 and have a duet just like helium. So lots of exceptions. These are the exceptions for ionic compounds. We'll get into more exceptions when we start talking about covalent. See if I can get rid of, oops. See if I can get rid of all that. Okay. So for main group elements, we can make Lewis dot symbols. And so, now I can't get my, give me a moment here. Okay, well, hopefully I've fixed it. Sorry about that. For main group elements, you figure out how many valence electrons something has, and then you'll place 1 dot per valence electron on each of the 4 sides of the element symbol. And then you will pair the electrons until all of the valence electrons are used. So here's what I mean by that. Nitrogen is in group 5A, and it will therefore have 5 valence electrons. And so we can write the valence electrons around nitrogen, please ignore that red dot, in a variety of ways. So we can write them like this, like that, right? It doesn't matter which side you put that lone pair on. It can go on any of the sides. But the way that I would do it is you have nitrogen, right? And we have 5 dots that we can use. And think about nitrogen as being in like a box. And so when we put dots around nitrogen, we're going to put 1 electron on each side before any get 2. Kind of like when we were doing electron configurations, right? We would put 1 electron in each orbital before any got 2 in those degenerate orbitals, like a p orbital. So put 1 electron on each side before any gets 2. You can't do something like this. Even though, yes, that still adds up to 5, right? It's not evenly distributed around the nitrogen. So here's some electron dot symbols for elements in periods 2 and 3. If it has less than 4, right? And so these ones like, sodium, magnesium, and these guys, if they have less than 4, you can kind of split them apart. Otherwise, I would just go around in a circle like they've started to do with aluminum and boron here. And then again, once you put 1 on each side, like we have for carbon, moving forward, then you'll start doubling up. When they have electrons that are sitting by themselves, they're not paired, these are considered to be bonding electrons. These are electrons that don't have a pair yet. They can participate in bonding. When you have electrons that are paired up, like these are called non-bonding electrons because they're not available for bonding. We will really commonly call them lone pairs. Okay, so if you hear me talking about lone pairs, that's what I'm talking about. So like argon has 4 lone pairs of electrons for a total of 8, right? Which is why argon doesn't make bonds. So we have a way of depicting ion formation, a couple ways. So the first way would be to use these partial orbital diagrams. So we have sodium and we have oxygen. And we know from ionic bonding, right, sodium will give its electrons to oxygen. Na plus gives you, and O2 minus. So that's how we're forming NaO. But we need 2 sodiums to give up their electrons so that oxygen can gain 2, right? So sodium will give up one of its electrons, but then oxygen still will need another one. So we need 2 sodiums here. So that sodium will give 1, that sodium will give another, and we will form O2 minus, right? And so this oxygen has this complete octet here. And Na plus will also have a complete octet. It's lost all of those valence electrons, and actually it will have 2s to 2p6, just like oxygen, because it lost that 3s electron. So this is one way of depicting the ion formation. You could draw these partial orbital diagrams to show it. You could also use the Lewis dot symbols, which I'm showing down here. So sodium would have 1 valence electron normally, and they would give it to oxygen to fill in, right? So oxygen has these 2 electrons that are available for bonding, and so if sodium gives, one of its electron to that one and one of its electrons to that one, now oxygen has a complete octet over here, and an overall charge of 2 minus, and the sodiums, right, have lost those valence electrons, but again, sodium would have a complete octet underneath that valence shell. So this is the 2 ways that we can show it. So if it asks for orbital diagrams, you would show it that top way. If I asked for, showing it through Lewis symbols, you would show it the bottom way. So similarly, right, we could, represent formation of ions using electron configurations. So if we wanted to form, lithium fluoride, Li plus and F minus. So here's lithium and fluorine. We know that lithium will give its valence electron to fluorine. So then we form Li plus, so that 2s1 electron is gone, and F minus, right? And so that 2s electron from fluorine, or from lithium, has now joined fluorine, making this 6 instead of 5. So that would be one way that you could show it. And then you could show it through orbital diagrams, just like we saw in the last example, right? Where lithium would lose that 2s electron and fluorine would gain it. And then you could also show it through the Lewis dot symbols, right? Lithium and fluorine. Lithium has 1 valence electron, fluorine has 7, and you would just show that arrow showing that lithium is giving its electron to fluorine, which leaves fluorine with a full outer shell, and lithium with that positive charge. So those are our ways of showing the electron transfer. So again, like I was saying earlier, ionic compounds are all forming these solid crystals at ordinary temperatures, right? They're always solids, and they're always crystals. And like I said before, there's a lot of different crystal structure shapes. This is when this one that we're showing here, this is a 1-to-1 ratio of, positives to negatives, but there are lots of different ways that these show up. But again, you can memorize those in a different course. So these ionic compounds organize into a crystal lattice, alternating positives and negatives. And so remember, our positive charges, our cations, are always the small ones. The anions are always the big ones. Okay. All salts are ionic compounds. So if you see this word salt, right, that doesn't just mean table salt, and we've talked about that before. The word salt is synonymous with the term ionic compound. right? All salts are ionic compounds, and they will all form crystals of one form or another. So this is a particular lattice structure, and the reason that I'm pointing out the fact that this is called a crystal lattice is that we have this associated thing called the lattice energy. And so the lattice energy is the energy associated with the formation of the crystal lattice of the compound from the gaseous ions. And so I want to make sure that we're looking the gaseous ions. And this will be important as we start talking about the Born-Haber cycle. We're going to have to, take our solids and turn them into gases and ionize them and combine them together and all of that stuff. But lattice energy, just by itself, the lattice energy is defined as the energy associated with the formation of the crystal lattice of the compound from the gaseous ions. So when the gases of Na plus and Cl minus react, that is what's the lattice energy for sodium chloride. So Coulomb's law, like I said, I keep talking about Coulomb's law. We're going to talk about it a lot. But as it relates to lattice energy, right, the energy of interaction between a pair of ions is proportional to the product of their charges divided by the distance between their centers. So like this. Again, these Qs, these are charges. So the charges of the two ions, and R is the distance between them, the radius. So again, we are going to want to have a very large lattice energy. We want large charges, and we want small sizes, small radius. Okay, so we want little tiny atoms or little tiny ions with really big charges to have a very large lattice energy. So lattice energy is the change in energy that takes place when separated gaseous ions are packed together to form an ionic solid. So when those two, right, that Na plus gas and the Cl minus gas, they react together and they form NaCl solid. Okay, so here I'll write that out. Na plus gas and Cl minus gas react to form NaCl solid. So the gaseous ions react to form solid sodium chloride. And so again, this is essentially the energy that we were just talking about, Coulomb's law. We want small ions with big charges to result in a really exothermic lattice energy. And when I talk about exothermic lattice energy, we're looking for a really negative number. So if we're comparing sodium chloride versus potassium chloride, sodium chloride would have a larger lattice energy than potassium chloride because sodium, right, is smaller than potassium. So again, we're wanting the smallest atoms with the biggest charge. And since all of these charges are the same, right, this is 1 plus, 1 minus, 1 plus, 1 minus, right, so we can't compare the charges, we can just compare the sizes. So since, the chlorine is the same, the only thing that's different is sodium and potassium. So since sodium is smaller than potassium, it will have the larger and more exothermic lattice energy. So here is some more examples over here on the right. All right, so if we look at sodium fluoride, this is Na plus, F minus, right? And so they're both, 1 plus, 1 minus. In the example below, right, we have 2 plus and 2 minus, right? So these are bigger charges, okay? And again, when we're looking at the most exothermic lattice energy, we want big charge, small radius. So since these have, the bigger charge, right? Oh, and if you have to pick between them, charge wins, okay? If you're like in this particular example, actually, sodium and fluorine are both smaller than, well, I guess fluorine is pretty similar to oxygen, but sodium and fluorine are smaller than calcium and oxygen. So the, and it's similar size. So the difference here is is from the charge, okay? So since calcium is a 2 plus and oxygen's a 2 minus, those big charges are what's making a really, really exothermic lattice energy. So the force of attraction between, lattice energy is the force of attraction between oppositely charged particles. It's directly proportional to the product of the charges. So the bigger the numbers on the charge, the larger the force of attraction. So large charge means the ions are more strongly attracted. So large charge, stronger attraction. A stronger attraction means a larger lattice energy. And like I said, of the two factors, the charge is more important than the ion size. So if you're stuck and you're trying to figure out between the two, if one of the pairs has larger charges, then that one is probably going to have a larger lattice energy. And again, here's, just to reinforce this, here's our table of ion sizes, just so you can reference it. Remember that things like, the cations, the larger the positive charge, the smaller that atom is. The bigger the negative charge, the larger the atom is. So here we've got just a couple more examples. So these are all, right, these are all chlorine. They're all chlorides. So the only thing that's different here is lithium, sodium, potassium, right, and cesium. These are all alkali metals. But as these alkali metals get larger and larger and larger and larger, right, as the size grows, the lattice energy gets smaller and smaller and smaller. Because again, to have a really exothermic lattice energy, we want to have a large charge. But when the charge is not changing, then we want to have a small ion size. And so since cesium is the largest of those alkali metals, it will have the least exothermic, right, the smallest negative number for its lattice energy. So here's an example. You can go ahead and pause and figure out, arrange the following ionic compounds in order of increasing lattice energy. So smallest lattice energy to largest. Okay, so what I would always look at first is look at the ion charge. So sodium is 1 plus, fluorine's 1 minus, cesium's 1 plus, iodine's 1 minus, calcium's 2 plus, oxygen's 2 minus, right? So if we're just looking at this, right, calcium oxide has the largest charges. That is probably going to be our highest lattice energy. Okay, so now trying to figure out the difference between sodium fluoride and cesium iodide. Cesium iodide has much larger atoms. Cesium is a very large alkali metal. Iodine is a very large halogen. These are large atoms. And again, to have a really exothermic lattice energy, we want small atoms. So these are very large atoms with low charges. They are going to have the smallest lattice energy. And then sodium fluoride, those are smaller atoms. They will have a larger lattice energy. And then again, calcium oxide has larger charges, so that will be a larger lattice energy. Okay, so what do we mean by lattice energy, right? So again, that lattice energy is the energy change when 1 mole of a solid in its standard state is formed from ions in the gaseous state. Again, that's this that I wrote down earlier. That solid is being formed from the gaseous ions. We just have a million different ways of saying it. Okay. We can use a process called the Born-Haber cycle to figure out the lattice energy, heats of formation, or other useful pieces of information about a particular compound, depending on what we're given. Okay, so the Born-Haber cycle is probably the trickiest part of this lecture, just to kind of, get your head around. So there you go. So the Born-Haber cycle is a series of hypothetical steps, and that we can use to calculate essentially, and their enthalpy changes, so their delta H values, needed to convert elements to an ionic compound and devised to calculate the lattice energy just of that compound. The lattice energy we actually can't measure directly, so we can go through and calculate it. In these Born-Haber cycle problems, sometimes it will give you the lattice energy, but just by definition, we actually, just out in the real world, we can't go through and calculate lattice energy, or we can't go through and measure lattice energy. We can go through and calculate it, though, by knowing a bunch of other things, which is where the Born-Haber cycle originates. But essentially, we're going to kind of use Hess's law as a means to calculate the formation of these ionic compounds, right? The combining of a bunch of different individual reactions to, calculate an overall reaction, right? That was Hess's law as we used it earlier. So just some kind of general steps. So if you have elements in their standard state, and you're going to convert them into gaseous atoms. So sometimes this will mean like breaking up diatomics, okay? So if you take, like sodium in its standard state is NaS, whereas chlorine in its standard state would be Cl2, right, as a gas. But in order to get the lattice energy, we need to, have them as gaseous ions. So at some point, if you're kind of thinking about this, we're going to have to take sodium and turn it into a gas and ionize it. We're going to have to take chlorine, break the diatomic, and then ionize it. So elements have to be converted into gaseous atoms, not necessarily molecules, right, like that chlorine gas. They will lose or gain electrons to form cations and anions, right? They have to be charged. And then we will combine the gaseous anions and cations to form a solid ionic compound. So our example here is the formation of lithium fluoride. So we have lithium as a solid, we have fluorine gas, and then we're going to make lithium fluoride. So you'll notice though that there's the 1/2 here, right? And that's because we are writing the formation reaction for lithium fluoride. And if you'll recall from before, anytime we're writing a formation reaction, we're always going to form 1 mole of our compound at the end, right? Whatever our product is. So we might have halves or other random fractions in the remainder of the problem. So one of the first things that we'll need to do is we will need to turn lithium from a solid into lithium as a gas. Okay, so this would be the enthalpy of sublimation. That's what that S here is. Don't worry necessarily about these zeros. That just means this. So the little 0 here, that means the standard enthalpy. So at a standard state or at a standard condition. But essentially we need the enthalpy, the change in enthalpy of sublimation. And so that is this value. How much energy do we have to put in to turn lithium from a solid into a gas? And then so that's taking care of making lithium into a gas. And then for diatomic gases like fluorine, we have to use the bond energy. So this term, this Be, this is bond energy if you're seeing this. Okay, also called bond enthalpy. So the reason, right, we only need, like when we're forming lithium fluoride, we only need one of those fluorines. We don't need both of them because we're forming LiF, right? And so that's why we're going to use 1/2 of the bond energy. So when we write this reaction here, we only need 1 fluorine on this side. So we're going to use 1/2 F2 gas, and we're going to split it and just have 1 F. So that's why we're using the bond energy here. And so just be careful. Make sure you only need 1/2. We only need 1/2 of the bond energy, even though, right, we have to put in the full amount of bond energy, right? The other one's going to float away. Just the way that we use it in our calculations, because we're only using one of the fluorines, we're going to use 1/2 of the bond energy. And again, this is going to be a positive value because we have to put in energy to split that bond. So after we've done both of these steps, right, we've turned lithium into a gas by using the enthalpy of sublimation, and we've split the diatomic by using the bond energy. Now we have individual atoms of those two floating around. So now we need to ionize them. So we have to form gaseous ions. So they're in gases, but they're not charged yet. So we'll deal with fluorine first. So we have electron affinity, right? Because fluorine needs to gain an electron, right? So you'll use electron affinity when you need to gain an electron. Okay, so this is the enthalpy change when 1 mole of a gaseous atom or anions gains electrons to form negatively charged gaseous ions. So they have to be in a gas before you can use this step already. So the way that we write this out is we have our gaseous fluorine is going to gain an electron and it will form F-. Okay, and then and it's still a gas. And so this delta H value, this is the electron affinity for fluorine. So now we've turned fluorine into an anion, so we need to turn lithium into a cation. So for here, we're going to use the ionization energy. This is when you're going to lose an electron, right? These are opposites. So this is the enthalpy change for 1 mole of a gaseous element, right? So it already has to be in a gas or cation to lose electrons to form a mole of positively charged gaseous ions. So the way that we write this is lithium loses an electron, right? It forms Li+, and that electron floats away. And so the delta H value, this is our delta H value for the ionization energy, is that. And so this is ionization energy 1, i.e. 1, because that's, the first ionization energy. So you could think of this one up here as EA1 as well, because it's only gaining 1 electron. Now, if you'll note, electron affinities are typically negative, and then ionization energies are typically positive. And then once we have both of these atoms in their gaseous state, we can go through and make our solids. So now they are charged, they are gases, and we can react them together. So Li plus F minus makes LiF. And again, like I told you, out in the real world, we can't actually go through and measure this. We only can go through and calculate this. So that's what it's saying here. It's always going to be really exothermic, right? This is going to be very, very exothermic. It's a very desirable formation, right? Because Li plus floating around and F minus floating around as a gas, those are not stable. But LiF as a solid is. And so the formation of that solid is really favorable. So it's going to give off a lot of energy, really exothermic. So again, we can't directly calculate this lattice energy, but we can figure out what the value is through manipulating Hess's law. So this is what we've done so far. We took lithium and we took the solid and turned it into a gas. This was the enthalpy of sublimation. And then we took fluorine and we split it, right? Instead of being, this should be just F. Sorry about that. So we split our diatomic. So this is 1/2 of the bond energy. And then we ionized our lithium, right? We pulled an electron off of lithium. So this is our ionization energy. And then fluorine gained an electron. So this is our electron affinity. And then this would be our lattice energy, which I'll abbreviate LE. But we don't know what that is, right? Because I told you we can't actually measure that, but we can calculate it by rearranging this. And then this is the enthalpy of the reaction. This would be like if we actually did the reaction, we can go through and calculate how much energy was being given off, right? This is negative. This is an exothermic reaction. But if you think about Hess's law, if we add all of these up, then it needs to equal that value at the bottom. So we can actually solve for what goes for the question marks, right? That lattice energy. So that's what it's doing here. So we have the heat of the reaction is equal to all of those things all added up. So you can, subtract and rearrange, and you can figure out the lattice energy. So there you go. Lattice energy for lithium fluoride is, negative 1,017 kilojoules per mole. It's very, very, very exothermic. So if you were to because you are responsible for knowing how to draw these. And so I'm just going to talk through this really briefly. I know it looks like a mess. It kind of is, but go through it methodically. You have practice problems in your lecture worksheet. And Alex will ask you questions about these problems. So know how to draw this. So here's essentially where we started. Okay, we started with our solid lithium and our gaseous fluorine. Okay, in our first step, we took lithium and we turned it into a gas. Okay, and that we had to put in energy to do that, so that's why the arrow is going up. And then we needed to split our diatomic, right? This step 2, we had to split our diatomic, half of the bond energy. And again, we needed to input energy to do that, so again, that's why our arrow is going up. Then once we have both of them in the gas phase, right, we have lithium as a gas and fluorine as a gas, now we need to turn them into ions. And so to ionize lithium, we had to input a lot of energy to pull that electron off of lithium. Okay, so that would be the ionization energy. And then once we've got lithium ionized, we needed to ionize fluorine. So that would be the electron affinity. But if you'll recall, the electron affinity for fluorine is negative, right? And so that is why this arrow is going down, because that's an exothermic process, right? So that's why this arrow is going down when fluorine gains an electron. And then now we have lithium charged as a gas, fluorine charged as a gas. Now we can react them together. This arrow here, this one is the lattice energy, right? Our gaseous ions are reacting to form lithium fluoride. So, and it's a very, very large negative number, so that's why we're having a very, very large arrow. And then over here on this side, this is the enthalpy of the reaction, right? And again, that was negative. This was our overall. Overall, if you add them all together, you get a negative number, which is that. And so we'll put our lithium fluoride solid just down here at the bottom. Okay, so you do need to know how to draw these. There are some problems on your lecture worksheet. I would really encourage you to go through them and get some practice drawing these. Oh, there you go. It can click through too. All right. Here's another way that the problems sometimes will show up. Estimating the enthalpy of formation for sodium chloride. So this is asking for something different. Okay, in the last problem we were solving for the lattice energy, this is asking for the enthalpy of formation. This is asking for the overall one, right? This one, like this value. It's asking for this, like what would go at the bottom for that Hess's law. So looking at this particular problem, right? If we're looking at sodium chloride, we have a bunch of things that we know. You're not going to be asked to like memorize these or even to look them up. They'll always be given. Okay, you just need to figure out how to manipulate all of these numbers in order to find what you're looking for. So if we look, right, sodium is a solid and chlorine is a diatomic gas. So at some point we're going to need to turn sodium into a gas and ionize it. And then at some point, we're going to have to take chlorine and split it, right? Split the diatomic, and then have chlorine gain an electron so that we can react them together, right? Our gaseous ions to form sodium chloride solid. So when we take sodium solid to sodium gas, right? We need, that would be the enthalpy of sublimation, sorry, right here. So we're subliming it, right? And that was endothermic. So if you were drawing this, that arrow would be going up. So these are a little bit different order than what I was doing before, but I'm just treating sodium into its gaseous ion and then treating chlorine into its gaseous ion. So sodium needs to be ionized, right? So we're going to pull one of those electrons off of sodium. So this would be its ionization energy. Okay, so we need to ionize our sodium. Again, that's positive. That arrow would be drawn going up because we need to input energy to pull that electron off of sodium. And then we need to split the diatomic for chlorine. We only need one of those chlorines, so we're going to use 1/2 of the bond energy. So be careful here. People will often leave out this half, but remember that we only need, right, based on our reaction up here, we only need one of those chlorines. So we need 1/2 of the bond energy. And then we're going to take our chlorine and we are going to ionize it. So chlorine is going to gain an electron. So we're going to use the electron affinity. And that one is negative. So if I was drawing this, then that arrow would be drawn going down. So essentially these would be going up, 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 and that would be kind of the top here, and then we would start going down from here, drawing those arrows. And now that we have our gaseous sodium and our gaseous chlorine, we can react them and form our solid, right? And so this here, this is the lattice energy, this -786. And again, that arrow would be going down. That would be our largest negative arrow because, right, it's a very, very large negative number. And then you could go through and double check, make sure everything cancels out just like it should, like Hess's law, right? And so once everything's canceled, you should have, your stuff that's left over, right? Our sodium solid, 1/2 our chlorine gas, and our sodium chloride solid. And then the way that we would figure out the delta H of formation, we would simply just add these up, right? Keep the positives and the negatives the way they are, and just add them straight down. But I'm going to caution you, because some people will be like, well, we just essentially took all the stuff in the table and we just added them together. True, kind of, right? But you do need to recognize we needed to use 1/2 of this bond energy here. So I would not just rely on like, oh, I'm just going to add them all up. Like that's probably not a good way to go. I would write out all of the reactions to make sure that you're doing it right. Okay. And that's the end. So that covers ionic bonding and the Born-Haber cycle. Please go through and get some practice on this Born-Haber cycle. Historically, people in this course tend to struggle with the Born-Haber cycle. You have problems, like I said, in the lecture worksheet, and also on Canvas, I've posted a link to Born-Haber cycle practice, and it will get you some practice doing these types of problems and solving for the lattice energy or the enthalpy of formation. So don't just assume that you've got it. Make sure you go through, put in the work, and as always, if you have any questions, please send them to me.